Just look at this. This is honestly one of your superpowers. I mean, sure, on the surface it looks like just like any other night, right? But the fact that you can see stars at all with the same visual system that operates during full daylight with no damage is honestly wild if you think about it too hard. How do your eyes know to adjust to different levels of brightness? How is it possible that I can make out so much detail at night when my supposedly advanced phone camera can barely go beyond a black screen? The best answer here, as always, lies at the molecular level. This is Rhodopsin, an ancient protein used by millions of different species on the Tree of Life to detect and react to light. This little blob in the back of your eye can help you detect nearly individual photons and adapt to wild shifts in brightness pretty quickly. If you take the time to understand how rhodopsin works, you'll get some ground floor insight into some of the most important biochemical fundamentals that power huge parts of your cellular landscape. And once you really wrap your head around that, you'll be able to look up at a night sky like this and know that in a very real way, this is the wider universe reaching out and actually touching you. It's time to break down your photoreceptors, y'all. Let's go ahead and get into it. And hey, welcome back to Clockwork. This is our second episode in an ongoing series about the molecular foundations of your senses. Subscribe so you don't miss a single episode, and please check us out over at watchclockwork.com or support this show on Patreon so I can keep making these videos. Anyway, let's not waste a single second. Let's just jump straight into your eyes. To tackle this, we're going to dive through roughly 3 layers of complexity. I'll be honest with you, all 3 of these are pretty satisfying and you can feel free to explore them as far as you want here. But it genuinely gets really satisfying if you stick all the way through the pathway level at the end, because we'll be able to put all these layers of complexity together and catch a brief and wondrous glimpse at how clever our biology is. So let's hustle. Time to speed run through the anatomy so we can get to the cool cellular and molecular levels. Speed running the anatomy here. You see, when light enters your eye via your iris, it's going to hit the back wall here, your retina. We're going to go ahead and skip a couple important layers of anatomy and find the very back wall of your retina, because who has time for more details like that? At the cell level, all the way at the back here, your retina is lined with a little forest of these column-ish cells called photoreceptors. You've got 2 main kinds of cells that can detect light, rods and cones. Most of your photoreceptors are rods, and they're there to help detect like ambient light and sort of like brightness itself. They're also mainly on your peripheral vision. And you might have guessed it from the image alone, but you've got 3 flavors of cones that are specially tuned to a color of light and therefore give you color vision. And we're going to zero in on our rod cells since frankly you have more of them and they're easier to animate for, reasons. Like a lot of the cells associated with your nervous system, your rods and cones are constantly maintaining an electrical charge about them. One of life's great superpowers is maintaining a difference in chemical concentrations between 2 sides of a membrane. Your rods polarize themselves through the action of a bunch of little gates. Here are 2 of them side by side. The first one, up top, is just wide open all the time. These channels are letting positive ions, particularly calcium and sodium, into the rod cell willy-nilly, no matter what. But if you look carefully, you can see these gates are held open thanks to these purple little guys. This is cyclic GMP, guanosine monophosphate. If the purple bit here looks familiar, that's because, yes, that's guanine, a nucleotide letter used to code genetic information. You might already know that your body converts some of your RNA adenine into adenosine triphosphate, the ATP that's used as your central energy currency. Well, spoiler alert, guanine's RNA form also moonlights as a kind of messenger in your cells. In the same way that you have ATP and ADP for energy, we're going to be dealing with guanosine triphosphate, GTP, in this video. Take the 2 phosphates off GTP and smash it together a little bit, and you're left with cyclic GMP. And here's the thing, we're going to deal with so many chemical names and acronyms that I'm just going to go ahead and immediately give up and call this one C-Gump so I don't end up beating you to death with jargon. If y'all have a better, more relatable name for C-Gump, y'all know I want to hear about it in the comments. But anyway, C-Gump is going to be stuck to this gate for a bit until some stuff happens to it later. If and when C-Gump happens to get pulled off of here, the gate's going to close. That's going to block calcium and sodium's ability to enter our rod cell freely, which really brings gate number 2 into play. This fella is way more active. Instead of just a wide open door, this is a pump that is constantly using energy to open and close. That action is constantly bringing sodium in, but actively pushing calcium out. The goal here is to basically balance the action of our C-Gump gate. C-Gump lets calcium in, and this channel will shove it right back out. And you know what? Another quick tangent here. This same kind of action is happening all across your body at kind of a brain-breaking scale. You know your body is constantly producing and breaking ATP to move energy around your cells. You churn through this goofy little molecule at an astonishing rate, effectively, roughly producing and consuming your full body weight in ATP every day. And here's the wild part, we can use that energy to zero in on something incredible. While you use ATP for basically everything, there is one process that far and away consumes the most ATP throughout your body during your day-to-day life. Fully a third, over 30% of the ATP your body runs through in a day is used constantly running these ion pumps, whether it's sodium-calcium channels like this or the more standard sodium-potassium pumps. Either way, the second place process isn't even close. And that gets me thinking. I used to think the meaning of life was ambiguous, a mystery even, but if you ask your molecules what the meaning of life is, it is abundantly clear from an energy standpoint and an energy usage standpoint. The meaning of life is, all else fails, keep the pumps running. So much of what we do depends on the constant, perfect balance of electrical charges across our cell membranes. So, make sure you drink your electrolytes or whatever. But anyway, let's zoom back out and see why maintaining that balance is so important, at least in our rod cells in particular. For us, we only really care about two main regions of this rod cell. The outer segment here is where the magic actually happens. This is a pancake stack of disc membranes chock full of little proteins that end up detecting light. And we'll talk about that in a second, but moving up to the opposite end of our rod cell is the ribbon synapse. This is where your photoreceptor passes along the light signal to be interpreted by your brain. And if you just watch this real fast, there's something really cool about ribbon synapses. They're basically always on. In dark conditions, your photoreceptors are using this little purple ribbon complex to constantly shove little bags of neurotransmitters into neighboring cells. These bags, or vesicles, are full of a neurotransmitter called glutamate, the same glutamate as MSG. Your photoreceptors are constantly pushing out a baseline level of glutamate, and when they detect light, they actually reduce that glutamate output. And it's the reduction in that glutamate that your brain is going to eventually interpret as a visual signal. So when you're not perceiving any light, the amount of calcium in your photoreceptors is high, and those ribbon synapses are able to keep the flow of glutamate up. However, when your rod gets hit by a photon, the C-gump on the calcium gate gets chewed up, and therefore the gate closes. This means the calcium pump has nothing counterbalancing its action, so the calcium levels in your rod cell will drop. This is going to hyperpolarize our rod cell's membrane, which slows the flow of glutamate out of the ribbon synapse. More light, less calcium, lower glutamate flow. The neurons attached to your rods and cones will interpret that interruption in the glutamate stream as a light signal, and boom, your brain gets the message. Nice. And hey, that's level 1. Light hits your photoreceptors, so they close these ion gates, causing your cellular pumps to drain that photoreceptor of calcium. With the calcium gone, the inside of the cell is now way more negative than the outside. That hyperpolarization causes this ribbon synapse to slow the glutamate flow, which the nerve cells attached to your retina will detect as a visual signal. Nice. But this story is about to get a lot cooler. So the main question we have to answer for level 2 is, what exactly is the light hitting? And now we're getting down to molecular town. Let's get it. But before we do that, let's get some sponsorship stuff out of the way first. This week's episode is brought to you by the good folks at the Curiosity Box, which is probably the single best Steam subscription box I've seen in ages. As a parent of a very curious post-toddler, my whole life has basically lived from STEM kit to STEM kit, so the Curiosity Box is a really great breath of fresh air. It's a big highlight here at Clockwork HQ. These kits come every 3 months, and each box is curated with hands-on activities that blend science, technology, engineering, art, and math, making learning both fun and engaging. Personally, I had a great time with their fall box. I cannot begin to describe the eruption of pure joy that hit our house when my 4-year-old beat me to solving this ambigram escape puzzle, and there's just so many cool little surprises in each individual box that we always find ourselves going back to. If you want to give the Curiosity Box a shot, Clockwork subscribers get 50% off their first box when entering the promo code Clockwork at checkout. Hit up the link below to learn more. But let's get back to this pathway. And so, let's go back up to these disc membranes, because we're finally ready to meet the star of the show. Once again, meet Rhodopsin. This little collection of helices is a foundational protein in a lot of different life forms on Earth. You can find rhodopsins all over the tree of life. In fact, an old school form of rhodopsin might have been the actual OG engine of photosynthesis used back in the days before chlorophyll was invented. And yeah, one day I'll have the time to do a video on the purple Earth hypothesis, but for now I'm just going to need you to Google that on your own time. So yeah, if we dig in one layer into these helices, rhodopsin is built around this little chemical called retinal, a very tense little molecule that can suddenly change its shape the instant instant it absorbs a photon. We're looking at the classic retinol in your rod cells, but all 3 of your cone cells are also stuffed full of this same rhodopsin. Your cone cells just manufacture different variants of rhodopsin that hold onto retinol in a slightly different way, making them more tuned to detecting different wavelengths of light. But what we're exploring today is just how that detection plays out. Basically, at the moment retinol gets hit with a light particle, a photon, its tail suddenly snaps out like this. And again, that's basically all retinol's job is. Your body basically squeezes vitamin A into this shape in the first place just so it can freak out when it's hit by a photon. Zooming out, that change in retinal causes rhodopsin to change its shape as well. And congratulations, that's it. That's how you detect light. And right now, that's enough for level 2. We now know that the retinal core of rhodopsin absorbs photons and kicks its little tail out. That little will cause this whole rhodopsin protein to change shape really subtly, which your photoreceptors will be able to detect as a visual signal. Nice. But that just doesn't answer everything. How exactly does that signal travel from rhodopsin to these gates all the way over here? Why haven't I mentioned sea gump or guanine in the past 10 minutes? Well, hoo boy. Now we get to level 3, the most complicated part of this whole process. Levels 1 and 2 were nice, y'all, but we're about to enter a whole new paradigm. Buckle up for the signal cascade if you dare. Let's get into it. Rhodopsin is actually just one part of a larger complex. If we pan down a little bit, we can see there's actually a lot more going on here. And that's because rhodopsin is actually a fundamental class of protein. This right here, this whole thing is a G-protein coupled receptor, or GPCR for short. Welcome to the bait and switch, folks. You clicked on a cool video about vision, but it turns out it was secretly just about biochemical fundamentals. All we're doing today is Leninger Chapter 12. For real though, GPCRs are such an incredibly important class of molecule. A complex just like this one can be found in most of your cells. You have around about 800 different GPCRs that are responsible for activating all kinds of signaling pathways. Fully half of the drugs currently in use across all of medicine are basically designed to either activate, block, or change how these receptors work, but most of them are activated by chemical signals. Like this one right here is the GLP-1 receptor that drugs like Ozempic and Mounjaro work on, that I'm sure you've heard maybe a lot about. GPCRs are ubiquitous because they are really good at transmitting signals across a membrane. Your cells need to stay self-contained in order to be, alive, but a lot of them also need to know what's going on outside. GPCRs are great for this. So yeah, GPCR receptors have 2 main parts. You've got structures like rhodopsin that are just a little bundle of helices that poke out of both sides of the membrane. The outside part either binds to a chemical or detects something else going on. That causes this whole complex to change shape, even the part that's down here inside the cell and in contact with the rest of the G proteins. That shape change is going to then activate the G proteins here. The interior G complex has 3 parts. G-alpha over here is kind of the main character of the group, but stays inactive while bound to the beta and gamma subunits. When G-alpha gets activated, it'll open up just enough to dump this signaling molecule it was holding on to. That's GDP. The less energetic guanosine diphosphate. I told you this is the guanine video, y'all. We weren't nearly done with it yet. Losing that GDP allows a more energized guanosine triphosphate, GTP, to swoop in and bind here. The full activation causes alpha to break up with beta and gamma, freeing these subunits to roam around the interior cell and cause all kinds of mayhem. Whatever that mayhem may be, it'll be enough to transmit our original signal across the rest of the cell. But look how long this video is. Why is this situation so complex in the first place? Can we just break up this G protein without needing the GTP? Well, here's the cool thing. G-alpha is really neat in that once it binds to GTP, it takes on a shape that's just a little uncomfortable for these phosphate groups. So after a short time, the tail end phosphate can't stand to be here, and it's gonna break off. Which means now we're back to our original GDP, meaning this G-alpha is no longer active. This inactivated G-alpha can reunite with the rest of the complex and wait for the next signal. This means that one little protein can transmit multiple signals over time. This gives your cell a critical amount of information. A single protein can transmit both where and when a signal happened by just being a little unstable like this. Cool. But exactly what kind of mayhem gets caused by activated G proteins? Let's just go ahead and roll through the rest of the entire signaling cascade kicked off by rhodopsin to illustrate. The signaling pathway that rhodopsin kicks off is pretty incredible, And if you take the time to really understand how your cells move this light signal from rhodopsin to your brain, you'll have a really good sense of how a huge portion of these complexes operate. But that's enough preamble, right? Let's break down this little relay race and discover just how powerful your visual system is. And so we're going to go through this step by step first, but then loop back around to check out some key moments where we can actually amplify this signal. Right at the beginning, light enters your retina and eventually makes it all the way down here, striking rhodopsin in its retinal core. Anyway, retinal gets all hot and bothered by absorbing that photon and kicks its tail out like this. Over the next handful of picoseconds, no joke, retinal's shape change pushes the surrounding rhodopsin enough to have it snap into a new conformation. And now we're off on the GPCR relay race. Rhodopsin bumps up against the alpha subunit, the transducin of these G proteins, which means it's time for this transducin to break up. The alpha subunit is going to hold onto this GTP and look for a new partner, while the beta and gamma subunits, sorry guys, we don't super care about what happens to you guys over here, so you're just gonna leave. All ruffled up, our transducin alpha bumps into another protein. This is cGMP phosphodiesterase, which, we're just gonna go ahead and label that PDE for now, for simplicity's sake. The shape of this activated T-alpha is perfect to bond to this little section of PDE, and then basically rip it out. We just tore the inhibitor out of PDE, and now this enzyme is primed to go buck wild on its favorite job, sucking up all the cyclic GMP it can and converting it into boring old nucleotides. Phosphates for days, lads. As PDE chows down on all that cyclic GMP it can, the concentration gradient here is going to collapse, making it very easy for cyclic GMP to stop binding to this ion channel and float freely in all this extra cell space instead. With all that cyclic GMP sucked up and leaving these channels, they're going to close. So when there isn't any light-stimulating rhodopsin, there's enough cyclic GMP lying around to keep this gate open and balance the action of our pump down here. But now that we've gone and closed that gate, the calcium concentration is going to fall quickly, causing our membrane to become hyperpolarized. Hyperpolarizing the membrane turns down how fast these ribbon synapses are pumping out that glutamate. Your ribbon synapse is going to slow down, and that's going to kick off a bunch of activity in the nerve cells and the rest of your retina, which will eventually allow your brain to interpret a single pixel change in brightness over a small part of your visual field. Kinda like this. This is what makes your retina such a powerful tool. By detecting small changes in membrane polarization, the same sensor can tell you the intensity of a light change. That helps make our vision incredibly sharp and your low light vision incredibly sensitive. But I'm going to get more into that later. Let's get back to that relay race. If we were just stuck in the on position like this too long, our rods and cones would be kind of useless. Now our molecular workers need to clear all this up so we can detect the next photon as quickly as possible. Back here in the disc membrane, there's a regulator waiting for this exact moment. As calcium levels fall in our rod cell, this enzyme down here is going to get activated by another protein that basically detects low calcium levels. This is guanylyl cyclase, a little printer that stamps GTP back into cyclic GMP. That cGMP then rapidly refills our rod cells so that these calcium channels can pop back open. So at the core right here, we have a setup for a gorgeous negative feedback loop. Turning this mechanism on causes cyclic GMP and therefore calcium levels to fall. Falling calcium levels turns on our cGMP printer, which immediately pushes the reaction back to its normal state. And yeah, I already hear you asking, but Clockwork, isn't PDE just chewing up all that cyclic GMP we're making? We haven't fully restored the balance here. How does that half of the process turn off? And this is the central beauty of GPCR systems. I'll remind you about the superpowers that these G proteins have. Remember, this G protein isn't going to stay activated forever. Eventually this GTP is going to break back down into GDP, which will turn this G protein back into its deactivated state. As soon as G alpha is deactivated, it's going to let go of the inhibitor subunit, letting it go right back to PDE, and that's going to stop the conversion of cGump. Problem solved. And that's one really important key here. The molecular machinery inside this rod cell is fine-tuned to repress the light signal. So the only way we can keep breaking up cGump is if there's an overwhelming amount of rhodopsins getting activated by a whole bunch of photons. Which means as far as your optic nerve's concerned, we're done here. We know how rhodopsin turns on the light signal, and now we see how the rod cell machinery turns off that light signal, so your eyes can tell you about differences in light over time. But independent of all this, there's one last secret step here. And this last step is what makes your vision truly powerful. Because this seems really inefficient, but independent of this whole signal, we actually have to reset each individual rhodopsin every time they get activated. Let's explore that real quick. We actually have to deactivate our rhodopsin as quickly as possible before things get out of hand, but I'll explain that in a second. Remember, this rhodopsin got activated by a fairly drastic shape in its core retinal particle. Small molecules like retinol aren't as wiggly as bigger proteins, so we're going to have to clip this guy out and replace it. But first, we have to disarm this rhodopsin. All Roddy has basically exposed themselves by being in this conformation, leaving them wide open to get tackled by another regulatory protein called rhodopsin kinase. The only thing RK really does here is jump on and leave phosphate groups on rhodopsin right here. This is a very common event across all of your chemistry called phosphorylation, and it's basically just tagging this tail end of rhodopsin, so another regulator called arrestin can detect it and attach here. Arrestin, get this, arrests the signal cascade by just covering up rhodopsin. Now this next part isn't fully understood, but arrestin also gradually helps old Roddy get rid of these 3 phosphates, and the word gradual here is key because we need time to clip this spent retinal out of the rhodopsin. For real, this part of the process can take over a minute and a half, which is brutally long enough on YouTube and positively glacial on a molecular timescale. But if we just fast forward real quick, eventually the spent retinal will break out of rhodopsin and eventually make it out of your photoreceptor and into the nearby pigment epithelial cells at the very basement layer of your retina, where a friendly worker called retinoid isomerase will beat it back into a useful shape. But anyway, back at rhodopsin, now that the spent retinal has left and we've got a new one locked in, arrestin doesn't really need to be here, so it'll disengage. And then we can just go through the whole loop again. Nice. Now, if that was the whole story, I guess it would be fine. But we glossed over a handful of key details that make your visual system truly special and truly powerful. I alluded to it a bunch, but arrestin needs to get here and cap rhodopsin as soon as possible. But why? This is a central power of GPCR systems. By having all these intermediaries, our cells have an easy time amplifying small signals into something detectable at a big scale. At the start here, activated rhodopsin can break up multiple G proteins. Basically, rhodopsin will break up any of these GPCR signalers it bumps into. And that brings us to the central disadvantage of using this view for learning this mechanism. Sure, it's nice and clear to review, but membranes aren't neat little lines like this. They are chaotic 2D planes. All of these membrane-bound proteins are free to zip all over the place across this plane, so rhodopsin can go hog wild and activate a whole bunch of G proteins, not just the one it was attached to at the start of this video. And then it gets even bigger because once the alpha subunit of that G protein activates PDE, that PDE will just stay on and chew up as much cGMP as it can until it gets inhibited. So your rod and cone cells already have 2 layers of amplification built in, making it possible for a single photon to activate one of your rod cells. Of course, you can't actually perceive a single photon, but our limit for detection is still incredibly small. People properly adjusted to the dark can report seeing a light signal as faint as a dozen photons. 12, which is incredibly small. But explaining why that happens will effectively double the length of this video. If you really want to understand that and get a better view of the molecular dynamics that power this amplification, I really recommend you check out the extremely strong video series that Dr. Carrie Kim produced about phototransduction. Find the link down below, or maybe it'll be in the top right corner, depending on what YouTube lets me do. So that's the first key. This signal is super easily amplified, but there's also key regulators in place as well. At the other end of this chain, recoverin is another incredibly important regulator that helps our vision adapt quickly to how bright things are. When there's a lot of calcium in your rod cells, recoverin binds to that calcium and is able to then inhibit old rhodopsin kinase. Now, if RK is deactivated, that means it can't tag an active rhodopsin, so therefore it can't get capped by arrestin, which means our active rhodopsin can stay active for longer and break up way more G proteins and make a way bigger signal from a way smaller light source, which is gigantic. And again, let's review this real fast because if you have a good grasp on this mechanism, you'll instantly see why that's important. To oversimplify, activating rhodopsin depletes calcium. More photons hitting this cell means calcium levels get depleted. On its own, this is awesome because that means our rod cell is actively putting out an analog signal. It's not only telling your optic nerve where a point of light is, a single rod can also contribute to telling your brain how bright a point of light is. But if this mechanism didn't have recoverin as a modifier, we wouldn't be able to see in the dark at all. Instead, as your eyes adjust to the dark and calcium levels rise to stabilize at a high level, recoverin makes your your rods more sensitive to weaker and weaker sources of light. To test this out, go ahead and go into a pitch dark place and let your eyes adjust over the course of a few minutes. As time passes and you're able to actively perceive more details and more shapes, keep in mind that in a way you are actively perceiving the concentration of calcium ions in your rod cells, kind of. That's what makes photoreceptors and the G proteins they're coupled to so powerful. A single input can convey a dazzling number of different outputs depending on the context. Our vision is not based in light itself, our perception is truly based in contrast, and that key distinction makes the vertebrate visual system astonishingly sharp. We look up into the night sky and truly we are only able to detect the stars above us because we have such a messy and complex signaling system powering our vision at the molecular level. Of course, we also glossed over a whole bunch of important information here. All the cells in front of your photoreceptors have to figure out a way to convert the over 120 million rod and code signals into something that the mere 1.5 million wires in your optic nerve can actually pass on to your brain. That is a wild bottleneck, and so many cool bits of neuroscience have to happen to get around it. But we've done enough just to understand the molecular science here, so let's go ahead and just wrap this thing up. Like I said at the beginning of this series, all senses are secretly touch, and I wanted to use vision to explain GPCRs because now I get to remind you that photons are in their own goofy and quantum way a physical object. So when I go outside and look up at night, these points of light are actually my physical connection to the wider universe. These points of light are the spare photons hurled out by massive stars billions and billions of miles away. They came all that way, and their eons-long journey ended by hitting a retinol on the back of my eyeball. You are welcoming an infinitesimal interstellar traveler every time you look up like this. And all you have to do to power it is make sure you eat a carrot or something so your body can make more of that retinol. That's what I really love about studying biochemistry, though. If you really understand what's going on at a molecular level, you can instantly connect it to such a wider process and have such a bigger piece of respect for what's happening here. But for me, those foundations are good enough for now, so we should just leave it at that. I really appreciate your time. Thank you so much. And hey, thank you so much for watching all the way through. If you like this video, please consider subscribing here and also check us out over at watchclockwork.com. This video is largely brought to you by my incredible supporters over on Patreon. Please consider joining them if you want to help bring these videos to life. This video in particular got a little out of hand, and frankly, it's a little frustrating to realize that this could easily have been 2 videos, which would have led to a more consistent upload schedule. But for the next few videos, I'm switching to punchier, quicker videos so we can get more consistent and get these uploads out quickly. If you're still listening to this, go to the comments and tell me what your favorite tree is, and that's also going to be a bit of a hint for what our next episode will be in about 3 weeks. Otherwise, one really huge way you can support the channel right now is checking out our partners over at the Curiosity Box. Find that link below. If that's not your speed, I would love it if you considered signing up for our email newsletter, where I'm slowly ramping up to getting weekly little mini Clockwork episodes out. Right now it's more bi-weekly and actually kind of paused because of how much rendering for this video got out of hand, but we are slowly ramping up to more of a bi-weekly and then weekly cadence as we also get up to faster videos. Either way, it means the world to me that you made it all the way through the end of this video. I would love to hear from you if you actually like extra long Clockwork episodes, or if you would prefer shorter ones. But either way, I really appreciate your time. But either way, that's going to be the end here for me. Thank you so much for watching. I really appreciate your time. And as always, I like to leave you with peace, love, and endless phosphorylation. Everyone be well. Thank you so much.